Hi everyone, this video is on the mixed exercise 9 question 4. We have the function f of x and we want to show that it is increasing on the interval minus k, and the task is finding the largest possible value of k. First of all, we need to remember that a function is increasing if its first derivative is greater or equal to 0. So this function is called increasing. Now in this case, the first step is finding the first derivative of the function. Then we can solve the inequality to find the values of a, the possible values for k. So this is a quotient rule differentiation, and in quotient rule we first square the denominator function and that stays on the denominator. Then we write down the denominator function times the derivative of the numerator function. So x differentiates to 1 minus, this time we write the numerator function times the derivative of the denominator function. So x squared plus 2 differentiates to 2x. And we can simplify this. So we are going to have x squared plus 2 minus 2x squared. This is then the numerator over x squared plus 2 squared, and x squared minus 2x is just minus x squared again, minus x squared plus 2 over x squared plus 2 squared. Now in order to solve the inequality, what we can do here is basically setting f dash x equal to 0, because we need to solve this in order to solve the inequality. So we can first solve this equation and use the roots to decide about the ranges for the inequality. So we have minus x squared plus 2 over x squared plus 2 squared is equal to 0. Then a cross multiplication gives us minus x squared is equal to minus 2. Then we can multiply both sides by -1 to get x squared is 2, which means x is equal to plus or minus the square root of 2. And if you go back to the main question, it was give the interval, and as you can see, this is the right form, because indeed the solution to this inequality is going to be the square root of 2 and minus 2. So what this means is that the value of k is equal to root 2, and the interval is minus root 2, root 2. Okay, for part B, we need to find the exact coordinates of the points of inflection of x. So in order to find the points of inflection of a function, we first need to find the second derivative, and then we can test whether the solutions to the equation of second derivative equal to 0 are going to be the points of inflection. So in this case, we need to find the second derivative. So the first derivative is minus x squared plus 2 over x squared plus 2 squared. So again, it's another quotient rule, and the denominator is going to be the same thing, but just a squared again. So we have x squared plus 2, and if we square that, since there is a square as well, it's going to be to the power of 4. So this is the denominator. So for the numerator, again, we write down the denominator function first, which is x squared plus 2 squared, and the derivative of numerator function is just minus 2x, then the entire thing minus, so minus, this time we write down the numerator function first, and this times by the derivative of the denominator function. It's a chain rule, so the power is 2, that comes down, and then the derivative of inside is 2x, and what remains is just the bracket and the power minus 1, which is just going to be 1. So this is the what we are going to have in the numerator, which is not very nice, but we can simplify that even though it's going to take a while. Maybe it's better not to simplify this for now, because we want to solve the equation f double dash x is equal to 0, right? And this might be helpful to just keep in this form for now. We can simplify later. Okay, so if we set the entire thing equal to 0, obviously the denominator, because of the cross multiplication as usual, the denominator will be gone, and we are going to have only having x squared plus 2 square minus 2x times by minus 2x, and then minus so here I'm going to take a factor of x squared plus 2, because this entire thing is going to be multiplied by that, so I can take a factor now instead of leaving that for later. So I'm going to have x squared plus 2, that this times by also, as a part of factorization, I also need the factor of 4x, because we have 2 times 2x times x squared plus 2. So if we have the factor of 4x, x squared plus 2, and then minus x squared plus 2 here is equal to 0. Now we can take a factor of x squared plus 2. So x squared plus 2. And even we can take a factor of minus 2x. So let's do that. Minus 2x times x squared plus 2. Then for the first bracket, we are going to have x squared plus 2 because of the power of 2. And then for the second bracket, we are going to get plus 2 times minus x squared plus 2. So these types of questions are very easy to make mistakes in. Be careful, because of the lots of algebra that there is. And okay, now we have this. We are at a position to solve the equation. But before solving, I think I can simplify this bracket one step further, so this bigger bracket. So we have minus 2x times x squared plus 2. Then for here, what's going to happen is that we have x squared plus 2, and then these 2 can be, we can expand this bracket to have minus 2x squared plus 4, and this allows us to simplify this now. So we are going to get minus x squared plus 6, and that makes this much nicer for the next step, because then we'll have minus 2x, x squared plus 2, and then minus x squared plus 6. Now is in a much better form. All right, now we have 3 different sort of brackets, and we need to set each of them equal to 0 in order to solve this equation. For the first term, which is minus 2x is equal to 0, then that means x is equal to 0 is one of the solutions. The next solution is x squared plus 2 is equal to 0, but obviously this doesn't have a real root, because x squared can't be equal to minus 2, so this basically doesn't have any solutions. And finally, we have minus x squared plus 6 is equal to 0, which is equal to x squared is equal to 6, and x is equal to a square plus or minus a square root of 6. So we found 3 different values for x. For the next step, we need to find the coordinates of the points of inflection. Now we have found 3 different values for x, and it's very easy to say, okay, these are all the x coordinates of the points of inflection. Let's just now find the y coordinates and then basically end the question there. But there is a big problem, because not necessarily all these x solutions that we found are going to be the x coordinates of the points of inflection. So not all of these are the points of inflection. But it doesn't happen all the time, because there are in some questions it just depends on the function. Sometimes the function that you're given, it's maybe a nice function, and the x coordinates you get, they're all going to be the points of inflection, and sometimes some of the coordinates are not points of inflection. So it's always safe to check them. because there is an easy test that you can check whether these are points of inflection. And that test is the second derivative test, basically. So you use the second derivative function, and then you just check the behavior of the function just before and after each of these x values. So what I mean is that I have shown this in many of the previous videos, and you can watch them in details if you like. But basically, let's pick x is equal to 0 first. So we are going to see what's the value of the second derivative just before, just after, and then just before that. So we basically add and subtract a very tiny amount to that root, and then find the value of second derivative at that point. So the idea is that if we get a positive and negative value, then that's fine. There is change of sign, and that means this is a point of inflection. But in the cases that it's not a point of inflection, we are going to get two same signs, maybe two positive or two negative numbers. The number itself doesn't matter, its sign matters. So yeah, as long as we get two opposite signs, then we are fine, and we can basically conclude that that's a point of inflection. Okay, now let's quickly do this for each of these points. So I'm going to plug each of these values in here because this is the nicest form that we got for actually, sorry, yeah, not here, because we need to substitute them into the equation of the second derivative. So this is not the equation of the second derivative, this is the one that we wanted to solve, because yeah, the second derivative is actually here, so that's not really nice. Okay, substituting into here when f double dash x is 0.1, we are going to get a positive value, and so to be precise, the value is 0.146, but 1.8, sorry, but we don't need to write that down, at least for this question, because sometimes the question is explicitly asking us to show that, but here it's just a quick test, so we don't really need to do that. We can just write if it's greater or less than to 0. And for the second one, when x is minus 0.1, we are going to get a negative value, and this proves that when x is equal to 0, this is indeed a point of inflection. So yeah, this is basically the quick test that I was talking about, and you're just going to repeat this for the rest of the values, because we have two more values. One is when x is root x, and the other one is when it's minus root 6. Sorry, I meant root 6, not root x. Yeah, so we are going to do f double dash x of root 6 plus 0.1, and then f double dash x of root 6 minus 0.1. okay, and not equal, because we don't care about the value right now, just the sign of that. Okay, for this one, when we have root 6 plus 0.1, we are going to get a negative value, and when it's minus 0.1, it's going to be positive. Again, we have another point of inflection here, and we need to check this for the last value of x, which is minus root 6, and see what do we get when we have minus root 6 plus 0.1, and when we have minus root 6 minus 0.1. And when again we have 0.1, it's negative, and when it's minus 0.1, it's positive. So just some boring calculation work. Okay, now that we know all of these three are points of inflection, again in this one we tested and we are now sure, but even if we hadn't tested, we wouldn't have made a mistake. Still, we can't skip that testing step, even though it takes a lot of time. The only time that I would say skip the testing is when you're in the exam and you don't have much time left, and even the question may not have that many marks. But yeah, if you don't have much time left and you think this is not a good use of your time, then maybe it's better to just whatever you get from the equation, just state that these are your points of inflection, and then find the y coordinates and move on. Otherwise, you should always check that. Okay, now that we know these are the x coordinates of the points of inflection, we just need to substitute each of these x values into the main equation, which is f of x, in order to get the corresponding y coordinates, and then that's basically it with this question. So when x is equal to 0, x is root 6, and x is minus root 6, let's see what are the y coordinates. So y and y is equal to, all right, so when x is equal to 0, obviously y is also going to be 0. And then when x is equal to root 6, it's going to be root 6 over root 6 squared plus 2, which is just 8. So that's root 6 over 8. And then when it's minus root 6, it's just going to be minus root 6 over 8. So here is minus root 6 over 8. Here is root 6 over 8. And here is 0. So these three are the points of inflection of f of x. Okay, that's it for this video, and thank you for watching.